Welcome everyone. It's a great pleasure to be able to give this talk. I would like to thank Professor Lee for organizing such a wonderful event. Today I'll be talking as advertised about scalar curvature and relativity. I'll give a snapshot. The relativity part will be slightly condensed. I'll focus mainly on the scalar curvature. And some of the work that I'll be presenting is joint with Ryan Unger and ST Yao, and there will be some kind of broad remarks and wider comments about the field as it is when it comes to studying the questions I'll introduce, which will be which manifolds admit a complete metric of positive scalar curvature. In particular, I'll compare and contrast some methods, and so I'll be speaking about other things than simply the result that we have with Ryan and Yao. So, what's the focus? Well, two questions really. Which manifolds support metric with lower bounds on scalar curvature? This sigma could be negative, could be zero, could be positive, doesn't matter. The question's interesting in all situations. And the other question will be, what other curvature bounds behave like a lower bound on the scalar curvature? So this is where relativity will come in, because in relativity, we'll study initial data sets, which are, of course, kind of Riemannian manifolds that embed a space-like hypersurfaces in Lorentzian manifolds, which are spacetimes, which are the primary object of general relativity. And owing to energy conditions one might impose on the space-time, in view of the Einstein equations, right, one might impose some energy conditions on the right-hand side of the Einstein equations, and that translates to lower bounds on the scalar curvature of the initial data set in a non-trivial way. So it's not a lower bound like this with a constant sigma, right? It's a lower bound that depends on all kinds of terms, but these are the two questions today. Now, here's some very broad background. Well, first of all, the Ricci curvature is a trace of the Riemann in the sense of the Riemann tensor, which incorporates all the curvature, and the scalar curvature is just the trace of the Ricci tensor. So this is a scalar quantity that's constructed out of the Riemann tensor by taking the trace twice. But geometrically, although this hasn't yet been used really to prove theorems, as Gromov notes in his survey papers, but geometrically, if you take the volume of a ball at the point P of radius r, and you expand this, right, in terms of r, then what you'll get is a term that's equal to the Euclidean volume for a ball of radius r, and a correction. Right, and this correction will have an expansion in terms of r, and the scalar curvature appears as the coefficient of the first non-trivial term. And what you can see is that if it's non-negative, then actually the volume of small balls is smaller than that of the Euclidean volume. And you know, if it's hyperbolic, so for instance, if the scalar curvature is negative, then this inequality changes direction. So essentially it measures the volume, right, locally. For products with metrics as such, it's simply additive. And an important fundamental result, which is not as elementary as these facts, which is actually much more interesting and much more difficult to show, but that was done by Shania in the 80s and Gromov in the 80s as well. Shania had a first article in 79, and they used kind of different methods. One is a PDE proof, the other is very kind of explicit construction. But anyway, if two closed manifolds admit PSC, then the connect sum of these manifolds admit PSC. And that's very useful when it comes to to classification, when it comes to looking for obstructions, and so on and so forth. So that's some basic background scalar curvature. As I said, the main question that we'll study when it comes to scalar curvature is which manifolds admit it, right? And you can see already by Gauss-Bonnet for closed two surfaces, right? So you can see already that the integral of the scalar curvature, which was the Gauss curvature, half the Gauss curvature, then that's topological invariant, right? So the integral over sigma. So if R is non-negative everywhere, then your Euler characteristic can't be negative, right? So that gives you a nice kind of indication that scalar curvature is related to topology. But more generally, the characterization for positive scalar curvature is known for two manifolds with or without a boundary by classical results. It's known for compact three manifolds by the resolution of the Thurston geometrization conjecture by Perelman. For compact three manifolds with mean convex boundary, and that's measured in the outward direction. So if I move the boundary outwards, then I increase the area of the boundary. Then that was done by Carlotto and Lee, and that result kind of follows from the previous one I said about the connect sum of two manifolds. And then for the spin K, if the manifold is spin simply connected and it's compact, then if the dimension is greater or equal to 5, a full understanding of what are the obstructions, etc., was achieved by Gromov, Lawson, Rosenberg, Stolz. But of course, many questions remain. So first of all, what about non-compact manifolds with or without boundary? So this question is much harder. I mean, it can be much harder because, of course, a lot of the proofs here use the compactness, and that really simplifies a lot of the arguments. So this question for non-compact is still very much open in many cases, even in 3 dimensions. The with or without boundary, I should mention that an arbitrary manifold with boundary, if no sign on the curvature of the boundary is imposed, then the scalar curvature can always be positive by a result of Gromov from the 60s, actually, I believe, the late 60s. So if you have a boundary, then you need some curvature conditions on the boundary, like the mean curvature or something. Right. So another important research direction is geometric inequality. So if the space has non-negative scalar curvature, then what kind of geometric inequalities can I expect for this space? So the positive mass theorem of general relativity is, of course, a fundamental example, but it's not the only example. The Penrose inequality is another one. Quasi-local mass, the whole subject of quasi-local mass in GR is another one. And then there's other kinds of geometric inequalities you might want to prove. And then there's rigidity as well. So there's rigidity in the positive mass theorem, rigidity in the Penrose inequality, rigidity in all these things. So we'll talk about that too. This is true not just in the context of GR, by the way. This is true for you can look at the inequalities like this for stable minimal surfaces or for minimal surfaces with Morse index 1, for instance. You've got rigidity in that setting as well when the scalar curvature has a low bound of this form. And then there's flexibility phenomena for R. So I'm really thinking here of kind of gluing results or interpolating between two scalar curvatures or results of that nature. Moduli space questions, of course, is a huge subject, right? So right, the question of which what does the space of PSC metrics look like as a topological space? What's its homotopy type, etc. So that's very interesting, often very difficult to prove results in this way, but there's some fundamental results in Ricci-Flow recently that appeared by Marquez, by Carlotto Lee, by Kleiner and Baumler, by various other people, and then the question of also which manifolds admit foliations by leaves which have PSC. That's another question you could ask. So these are all interesting, and there are various tools to study these things. classically, possibly the first tool came from index theory. So for compact manifold, at least, we have the Atiyah-Singer theorem, very powerful result that tells you that the topological index associated with some operator D is equal to its analytic index. Now, topological index is defined in terms of K theory, etc. And I won't define that, but the analytic index is quite simple. It's just the difference of the dimensions associated with D in the kernel and co-kernel. And so by the Lichner-Eritz Schrödinger Weizenbach type formula, you've got the scalar curvature appearing here in the square of the Dirac operator, and so it follows that if it's everywhere positive, the analytic index is actually 0. You can see this for just a one line computation, and that means the topological index must be 0, and so that gives you information about the topology of your space, and this method is kind of developed into its own field. I mean, there's a whole field of this kind of applications and these kinds of methods and tools. And parallel to that, and in a way that still hasn't really been kind of combined or synthesized, and there may not be such a clear relation between the two, but is the kind of geometric measure theory approach, where you kind of manipulate hypersurfaces within the manifold. Now, these hypersurfaces will, they may come from some minimization procedure or some other thing, but this method is what we'll be talking about in this talk. So this is what I'll be talking about solely. So manipulating hypersurfaces. And what's interesting is that this technique and this technique are kind of the two fundamental techniques, but they're kind of, they're good at doing different things. They have drawbacks and advantages in various types of questions, various types of settings. Some things I should mention as well is that, I mean, conformal deformations to the metric lead to a formula for the change in the scalar curvature, which looks like this, where L is this operator associated with the conformal factor. And the interesting thing here is, of course, that this Laplacian shows up, and so understanding the positivity of this or the constancy of this ends up amounting to a problem in elliptic PD problem, which of course can be studied from all kinds of all sorts of angles and tools. And then geometric flows have been used to study scalar curvature, of course the Ricci flow, as I mentioned before, but conformal or inverse mean curvature, even mean curvature actually has been also used in the context of general relativity in initial data sets. So you can use geometric flows, and then there's other tools which I know very little about. I won't be speaking today at all, but that's come from Seiberg-Witten theory or non-commutative geometry. So today we're really talking about this one, right? How to manipulate hypersurfaces, and this. So before I go on, I think I want to just recall a kind of dream by Gromov. So he's really kind of reinvigorated the field of scalar curvature, I would say, from various angles in the last 5-6 years, with papers, deep, difficult papers appearing, regularly, right? In 2014, 2017, 2018, 19, etc., 2020. So he's really produced a lot of problems and ideas and conjectures in scalar curvature. Now, in a long survey in his 4 lectures, IHES lectures, he says, the most tantalizing aspect of scalar curvature is that it serves as a meeting point between 2 branches of analysis, the index theory and the geometric measure theory. Each one of these theories is its domain of applicability to the scalar curvature problems, with a significant overlaps and distinctions between the 2 domains. So this is what I was saying before. And this suggests, on the one hand, a possible unification of the 2 theories, and on the other, a radical generalization or several such generalizations of the convex space with scalar curvature bounded below. So there's really a lot of hope here in Gromov's dream, and I think he's trying to emphasize here that we still don't understand scalar curvature. Right. So we're going to be manipulating hypersurfaces. These are going to be prescribed mean curvature hypersurfaces. So they'll either be minimal surfaces or marginally out of trap surfaces from general relativity, or mu bubbles, as Gromov once called them. And now I think the terminology is stuck. So these are kind of some of the results that I'll be talking about. And that are the kind of 2020 results using these kind of techniques. So Chodoshli have a wonderful paper proving that closed aspherical 4 or 5 manifolds do not admit PSC. They also show in this paper that if a closed manifold has the structure of a Shania manifold, something I'll define later on, and a S1 over an S1 product, right? So if that connects sums with some arbitrary non-compact manifold X, then that doesn't admit complete metric of PSC. At least for dimensions 3 to 7. Of course, the 7 comes from the problem that plagues higher dimensional, right? So minimal surfaces can have singularities when dimension is 8 and above, and so these proofs kind of don't work in that setting. But at least when the regularity works out, these two results are kind of wonderful and remarkable contributions by Chodoshli. Gromov remarkably actually proves even more. He shows that this kind of aspherical result can be generalized to what he calls uniformly acyclic spaces and maps. And when you have a manifold that admits non-increasing maps of non-zero degree to these types of spaces, so they don't have uniform PSC in this case. So I think it's a truly remarkable result and a truly remarkable set of results. With Ryan and Yao, we proved something slightly different, but in this direction. So we showed that at least for n is equal to 3, then SYS connects sum xn does not admit PSC, and then when n is between 4 and 7, if the non-compact factor is assumed to be lambda rho contractible, which is something I'll define, essentially means that all rho balls are lambda Lipschitz contractible. Well, I'll define that a bit more carefully later on. But these manifolds, these connect sum of SYS with X, do not admit PSC. So notice that the Chodoshli theorem has an S1 in it, which comes from, you can see that appearing in their proof. You can see how that comes about. We don't have this S1 factor. So in one sense, it's more general, but actually we have this lambda rho contractibility, which is a very strong assumption about the structure of the manifold, and kind of kills the non-compactness in a way. So these two results are complementary, but actually they leave open the question of the cleanest version of these results, which just says Shania connects sum with arbitrary manifold. Does this admit PSC? So this is still open. Now, it may be that techniques of Gromov and Chodoshli, along with our techniques, possibly will lead to a resolution of this. It may be that this is known to some people. It may be that that this will be shown. But trying to solve this using the methods of Chodoshli looks promising, but it's not quite obvious from their arguments that you can do this. But anyway, so how do these, before I go on and explain some of these techniques and how they work, we have to go back to some classic arguments and just understand what the classic arguments say. And this comes back to Shane and Yao in 79, really. The descent, or Shania descent, kind of technique, as Gromov calls it, is something like the following. You suppose, right, you start with an orientable closed manifold with PSC. Well, then if n is less or equal to 7, then the regularity tells you that any non-zero homology, so integer homology class, n-1 is represented by a collection of compact-oriented hypersurfaces. That's something to do with geometric measure theory that was known a long time ago. It comes from the 60s, essentially, with the work of Herbert Federer, Fleming, And the point is that once you've minimized in the relevant homology classes, you get this regularity, and then with this regularity, because it's also a minimization problem, you get the stability inequality. Right now, the stability inequality is huge, because that tells you that essentially on sigma, the following inequality is true, and this is the inequality you get when you compute the second variation of area in the direction normal to the hypersurface. So nu is just normal to sigma, and A is the second fundamental form. So, and Ricci is with respect to the ambient metric. Now, by using the Gauss equation, you can rewrite the Ricci term as follows, and then H disappears if it's a minimal surface. All right, so H goes away, and then you can just rewrite this inequality and play with the inequality until you can show eventually that sigma is Yamabe positive, so it admits a metric of positive scalar curvature in its conformal class. Once you do that, if the homology of the manifold is organized in the right way, so at each level you can keep minimizing in the homology class, then you'll eventually produce something that's Yamabe positive and two-dimensional. But if that class isn't spherical, right? By Gauss-Bonnet, you know that it has to be a sphere. Then you have a contradiction, right? And so that's the idea behind this kind of, right, the torus theorem, if you like. So that was the proof given by Shania in '79. So the general case was covered by Gromovs Lawson in the 80s, 1980. But the recent preprint of Shania will enable us to go beyond this, right? Because they essentially explain how to get rid of the singularities, or how to go around the issue of singularities, at least for these types of problems. So here's a torus. Here's a two torus. Here's a two torus. I'm minimizing the homology class of this two torus. I produce sigma, and then sigma. I can vary sigma normal to sigma. I will have the stability inequality because it's a minimizer. Once I have the stability inequality, I can massage it to make it to show that it's Yamabe positive, and then since it's a two torus, that's a contradiction. And this argument just works by induction as you go down the levels up to 7, and then above 7 you have the issue of your singularities. So anyway, that's how you do that. And then this is just a kind of more wordy version of what I said, a more general version of what I said. So rather than taking the torus, which has its homology organized in the right way, you can just put forward the following definition. So something is Shania-Schick if it emits a smooth map to a torus n minus two-dimensional, such that for a generic point, the embedded surface is a homology class which is not in the image of the Hurwitz homomorphism. That simply is to say that it's not spherical, and then if it's not spherical, once you've done your induction, you get a contradiction because Yamabe positivity is preserved at each step in the induction. So this class of manifolds is kind of a cleaner way of, or is just presented to you by the proof, right? By the idea of the proof. So this is the theorem, obviously, that's shown in the Shania 79 theorem, although it's not treated quite like that. And then again, there's this general N that's looked at by Shania and Lohkamp. And now, what has this got to do with relativity? What has this got to do with mass, ADM mass, etc.? Is going to be the subject of the remainder of the first part of this talk. So a complete asymptotically flat 3-manifold has scalar curvature non-negative, and then one shows that the ADM mass is actually non-negative and 0 if and only if G is flat. So this is an asymptotically flat manifold. Each end here is, has the structure that outside a compact set. It's diffeomorphic to R3 minus a ball, and they are connected in this way. And the ADM mass is a quantity that's taken as the integral of certain terms here, if you like. I haven't written them down, but essentially involve derivatives of the metric. And the point is that this integral is taken over 2 spheres, which get larger and larger. in the limit as r goes to infinity, and this converges if the manifold has the right structure. If the metric approaches the Euclidean metric at the right rate, and it actually ends up being a geometric quantity. So although it's defined in terms of these coordinates, it turns out that it's geometric invariant, but that's not obvious. You have to show this. That was done by Bartnick and Crucial in the mid 80s, 86, 88. And so, you know, showing that this mass is non-negative was a big open problem, and Shania resolved it. And they also have the wonderful rigidity that is zero if and only if G is flat. So how does the original, I go through the original Shania argument because I think it's relevant for what's to follow. There are different proofs. There are spinor proofs. There's a proof by Witten. There's refinements of this proof by Witten, explanations of this proof by Witten. So there's other ways to approach this, but for the purpose of this talk, I'll go through this proof. So, well, the first step I haven't written, which should really be step 0, is that you move from the manifold you have to something that has a nicer asymptotic structure that makes these arguments kind of work better. But I haven't mentioned that because it's not relevant for now. But anyway, assuming the mass is negative, you can end up showing that right, these planes, these coordinate planes, are bent in the right way, so that you can look at a cylinder and then obtain a solution to the plateau problem along this cylinder, right? So that's a disk, a minimal disk, and of course this minimal disk is stable because it's a minimization problem. And then as you build larger and larger cylinders, these solutions to the plateau problem, you know, they go out to infinity. And eventually, you know, you can show that these converge to a hypersurface. Now, the stability inequality is true at each step. And what you can show is that in this process, you end up with a stability inequality on this hypersurface. And then you manipulate the stability inequality in a very clever way to eventually show that there's a contradiction with your assumption on the mass and the scalar curvature. So that's the original Shania argument. And what's kind of remarkable is that in a paper in '99, Lowcamp showed that actually, suppose you had an asymptotically flat manifold and the mass was negative, and the scalar curvature was non-negative, then in fact you could produce a manifold which compactifies the other ends, and that is actually a compact manifold now, and the connect sum with a torus, n-dimensional torus, and you could produce a PSC metric on this manifold. And, well, I mean, this should be non-negative, but and strictly positive somewhere. So, which then you can deform to strictly positive. But anyway, the point is that suppose the mass in this end is negative, then you can 1-point compactify the other ends, using the asymptotic structure that these other ends are going to satisfy. And by solving the PDE, you can actually produce a metric which is flat on this end outside of a compact set. So that's what G equals delta means here. And then by identifying these these faces in the usual sense of the torus, then you produce a closed manifold with PSC that has the structure of the compactified other ends and the connect sum with the torus. Now, of course, this is not allowed by the Shania argument. So the positive mass theorem ends up being a corollary of a geometric theorem, which tells you about the PSC of closed manifolds. Right, and that's remarkable because, of course, in the previous Shania, we had to do the asymptotic analysis, you know, fully engage with the non-compactness of the space, whereas here you kind of reduce it to a geometric theorem. But essentially, that's part of the interest in these results of proving things about connect sums with particular types of manifold. And in a little more detail, the result with Ryan and Yao is that if SYS connects sum with X, and X is now arbitrary and possibly non-compact, so not like in this setting where you have a compact manifold, but this factor here is now could be non-compact, and this factor here is now not just a torus, but it's an SYS manifold, well, then we prove that indeed, if n is equal to 3, or if n is between 4 and 7, and x is lambda rho contractible, then you don't have PSC on such manifolds. And this is just a kind of explanation of the definition of lambda rho contractibility, just in a little more detail. So again, as I said before, rho balls are lambda Lipschitz contractible. So that's the results. And the sketch of the proof, I'm going to go through the proof, but just I'm going to sketch it out, because then later I want to compare it with a different argument. So this is the SYS factor. These are the right non-compact X, if you like, could have lots of n's, could be doing all kinds of things. Well, you consider a compact exhaustion of this X. You deform the boundary of these compact sets to make them mean convex. When you do so, you may incur a loss of your scalar curvature positivity in a neighborhood of the boundary, but that's going to be irrelevant because you're eventually going to send this guy to infinity. Once you've done this, you can minimize in the n-1 homology class provided to you by the SYS factor. So there's homology up in here, right? So for instance, like this, and as I minimize, well, you can see I've drawn, in green here and then in red later on, what the minimizer looks like at each step. Then you kind of have to show by a kind of topological argument that as you take this exhaustion, as you go up the family, your minimizers can't, if this is the surgery sphere, right, for this connect sum, your minimizers can't fully escape a neighborhood of the surgery sphere. So they can't fly off to be represented by cycles all the way up here in the ends. They have to somehow be anchored in the neck here. This anchoring, along with a kind of with the isoparametric inequality, actually enables you to show convergence of the sequence of minimizers sigma I. So notice now the resemblance, right, with the Shania proof of the positive mass theorem. You minimize and you take a sequence, you show convergence. Each minimizer is stable. That stability gets inherited in the limits, and then you play with the stability inequality of the limiting hypersurface. In the n equals 3 case, you've got strong results known for a long time now about stable minimal hypersurfaces in PSC manifolds, and you can get a contradiction relatively straightforwardly. In higher dimensions, the minimizer is in general non-compact, and dealing with these hypersurfaces is hard in general. So we assume lambda rho contractibility in order to show that if actually the limiting hypersurface sigma ends up being compact, and then the induction proof follows. Well, is the rest of the argument. So that's the basic idea of that's the basic sketch of the proof. And now I want to talk about mu bubbles, right? Which are different, which are kind of a different and in a way finer kind of way of doing this argument, because what you do there is, rather than face the consequences of the non-compact space, you minimize a different problem, which will somehow incorporate the non-compactness of the space. So I'll describe very briefly what that is, but as I'll show as well, this argument doesn't actually give you the full SYS connect sum result, but I mean, it may do. It may be it may do with sufficient tweaking of their arguments. But anyway, so this is what they prove. If there's an S1 factor, then you can get rid, from the dimensions 4 to 7, you can get rid of lambda rho contractibility, right? So it's a very nice result. And the way it works is, well, first you set up a manifold. So this MG isn't the original, isn't the manifold itself. It's some subset of it, some specific subset that you've created. Perhaps you passed to a cover, perhaps you've chopped off some ends you don't like, whatever. But you identify these boundary components. You have to choose them carefully, of course. But you end up doing the following thing: you construct a function h that goes to minus or plus infinity on these boundary components, and then you minimize a different problem. So you don't just minimize area within a homology class. You minimize this kind of area minus volume weighted by H, and all of this warped by U, right? So this is a kind of more complicated version of n-1 volume area minimization, if you like. But the lovely thing about this is that because H is being sent to plus or minus infinity on the boundary, as I've done here, it stops the minimizer from escaping into regions where you wouldn't want it to go. So, you know, if I had an end here and I was worried about the minimizer flying out as I minimize in some homology class, which is what we would have done before, this H penalizes the surface from flying out into here. So that's the clever idea of the mu bubbles, right? It's that you penalize, you handle the non-compactness by penalizing your hypersurfaces from flying out into the wrong regions or in the regions you don't want it to. You have to prove, of course, existence and regularity of the minimizer of this problem, but that's doable once you've set up the problem, right? And then the first variation will give you, of course, the mean curvature of the hypersurface sigma, which may be disconnected, may have different connected components, but you get this formula for the mean curvature. So notice that H appears here, and mu was the warping that appeared in the function. But crucially, when you compute the second variation, which was the equation, or which was the inequality I showed you on one of the first slides, right, when I showed you about the Shania technique, right? So when you compute the second variation with this new functional, you get something much more complicated. I mean, you get a lot more terms here. But if you're sufficiently dexterous about how you set up the problem, you can actually control all these terms to your advantage, and end up proving a contradiction. So that's exactly what Chodosh-Lee do. So in the aspherical case, they have to work very hard to prove their beautiful theorem. But in the case that I'll describe, or that I'm describing here, will actually take U to be 1. So this term just disappears, and large H is equal to small h. This term goes. This term is just 1. This whole term dies. This whole term dies as well. And then this is just 1. And so you end up with this term and this term as your relevant terms. And this is the trace-free part of the second fundamental form. It's usually written with an O, but I've written it with a hat. Anyway, so if you look at these terms here, then if you construct your H such that the following inequality holds, then you can manipulate this stability inequality to put the relevant terms you want to on the right-hand side. And then you end up showing that this is true. So that the gradient of phi squared plus half the scalar curvature of sigma squared. But this is exactly the kind of thing that tells you that your sigma is Yamabe positive. So this mu bubble trick, by constructing the right H, you end up proving that your hypersurface sigma is Yamabe positive. And if you've engineered if you set up your problem right, so that this should give you a topological contradiction, then you're done, right? So that's the idea of how to prove the Shania-Schick S1 theorem. But you might say, okay, well, why is the S1 required? Well, it turns out that the setting up of the problem and the construction of H, etc., is done most straightforwardly when you have this S1. You can kind of unwrap the S1 to an R to the real line, and you can work with a cover and do the wonderful things that Chodosh and Lee do in their paper. So anyway, that's how that works. So I guess the non-trivial part is really the setting up the problem so that you can actually do this argument, and that's not obvious for the without the S1 fact. So now I want to talk a little bit about applications to conformal geometry. I mean, I told you a little bit about the positive mass theorem, why it's related to like the torus theorem, or things like that. But there's also applications to conformal geometry, and that actually comes from a paper of Shania in '88. So there are two kind of classic theorems, Liouville and a theorem of Cooper. So essentially, if you have an open subset of Sn, then a conformal map to Sn with respect to the round metric is a restriction of a conformal diffeo, which is a composition of an isometry and dilatation and inversion. And then Cooper shows that actually, well, if you're simply connected and locally conformally flat, meaning there's a locally conformally flat structure on your manifold, then there exists an immersion which induces the locally conformally flat structure on M by pullback, and it's unique up to conformal diffeomorphisms of Sn. But so we have an immersion, and now the question is, when do we have a diffeomorphism onto its image, right? So the injectivity of phi is an interesting question you might study, you might like to ask. And Shania actually proved a wonderful theorem. They showed that, well, if Mg is a complete Riemannian manifold with non-negative scalar curvature and phi is a conformal map to Sn, well then the injectivity of phi is equivalent to the positivity of the energy. And the energy is a quantity they define as the ADM mass associated with the blow up of the metric using the Green's function coming from the conformal Laplacian. So here is my manifold. Here is a point P. I consider the Green's function for the conformal Laplacian, right? The conformal Laplacian was what arose in one of the first slides, coming from the transformation of the scalar curvature under conformal change of the metric. Now, this has a pole at P and it blows up. And by multiplying the metric by the Green's function on approach of P, you end up opening up this region into an asymptotically flat end. Now, you do so in such a way that the metric is sufficiently nice that you can define a mass, right? And that's just something that you can check, that this produces something that's good enough to have a well-defined mass. And then what they show is that if this mass is right everywhere positive, then actually phi is injective. So there's this wonderful interplay between the ADM mass and the problem in conformal geometry. So then, once you've done that, you can ask the question, well, when is this energy positive? And Shania actually went into the ambitious kind of conjecture that actually the positive mass theorem, which was previously something about asymptotically flat manifolds, which means, right, that outside of a compact set, each connected component is diffeomorphic to R3 minus a ball, then take out all the other ends and just suppose that you have one asymptotically flat end. So this end could be doing, all kinds of things. This could be a cusp. This could be cylinder. This could be hyperbolic. You've got no control on this. Well, then they say that actually, these other ends don't matter. If the scalar curvature is non-negative, and you have one end which is asymptotically flat, then the ADM mass of this end is non-negative and zero if and only if n is flat. So this is what you might call the positive mass conjecture with arbitrary ends. And the validity of this conjecture would immediately imply the injectivity of phi from the Shania result I just mentioned. And that makes it interesting. Now, what we show actually in our paper with Ryan and Yao is that you don't have to prove the positive mass theorem with arbitrary ends to prove the injectivity of phi. It turns out that by kind of looking at Lohkamp's compactification trick, you can cheat a little bit, do away with having to prove the positive mass theorem with arbitrary ends, and you can actually just show that the injectivity of phi just follows from the impossibility of a PSE metric on torus connects some yn, where yn is is arbitrary. So this should be xn. I've used xn the whole way through the talk. So apologies. This should be that. Should be xn. So that's what we show, and then it follows then that if xn is lambda rho contractible between dimensions 4 or 7, then phi is injective. But of course, because Chodosh-Lee prove it without this lambda rho contractibility, so long as you have this S1 product, but this S1 product is clearly true of the torus, then actually Chodosh-Lee fully resolve the Shania right, injectivity of phi without making assumptions on xn. Right, so that's the end of the first part of my talk. Thank you all for listening, and I will see you shortly for the second half.